So when we talk about the ion exchange chromatography method, since we are targeting the protein molecules, we'll have to understand the charge characteristics of the protein molecules. Okay, so we'll just talk about biochemistry of amino acids or proteins just briefly. Okay, so proteins are made up with amino acids, right? There are 20 different kinds of amino acids out there. Okay, whatever those amino acids are, they have the simple structure. Okay, alpha carbon carboxyl group, hydrogen, and then amino group, and side chain. There are 20 different kinds of side chain there. Okay, so amino acid has those two charges. Carboxyl group is negatively charged, and amino group is positively charged. Okay, and then side chain could be charged or not charged or polar, non-polar. Okay. So since your proteins are made up with a bunch of these amino acids, of course your protein will be charged kind of differently. Okay, so based on what amino acid you have, if they are charged negatively or positively or polar, your protein's charge characteristic will be determined, right? So that's probably a well-known fact. You understand that. So let's talk about acid-base chemistry of your amino acid. Okay, so if your amino acid is presented to the different environment, for example, okay, so your amino acid could be charged differently. Okay, so let's say whatever this amino acid is, because it's hidden, the I group is hidden, we don't know what it is, but if it is presented in a surrounding environment that is pretty acidic, that means acidic means what? Its environment has a lot of hydrogen ions, right? Then those extra amount of hydrogen ions will interact with the amino acid, so COO minus will be bound with hydrogen ions, so it'll be neutralized, right? But NH3 plus will always exist at NH3 plus. So under this circumstance, your protein will be what? Positively charged, right? But as you change the pH of its surrounding environment, okay, let's say you're bringing up the pH to neutral, about 7, then what's going to happen? You are reducing the amount of hydrogen ions, right? So since hydrogen ions are going away, maybe one of them is taken away from here. So from this conformation, your protein can become this, okay? So now COOH was changed to COO minus, and this may stay as the same, NH3 plus, okay? So now overall, this amino acid what? Negatively charged, positively charged, so they may be neutral because negative, positive kind of cancel each other, right? So let's say you're increasing the pH again. Increasing pH meaning what? pH 8, 9, 10. So your hydrogen ions will be less concentrated. So you're taking away hydrogen ions again. So then you can take one hydrogen away from here. So NH3 plus will become NH2. Not charged, right? And COO minus will stay as CO minus. If you look at it, the overall amino acid will be what? Negatively charged. So what it says is here is what? Depends on the pH environment of your amino acid. Your amino acid could be differently charged. Under the very low pH, it may be positively charged. Under the neutral condition, it may be neutral. Or under the high pH condition, it may be negatively charged. Okay, so your amino acid can be charged differently based on its pH environment. That's what it means, right? So we say the pKa, okay, values where your amino acid will be differently charged. Okay, so we know where your amino acid will become as neutral. Okay, that's a pK1 plus pK2 divided by 2. That's the pH value where your amino acid will be neutral. Okay, that is PI, isoelectric focusing, or isoelectric point. So that's the pH value where your amino acid will be neutral. So you need to know what that pH value will be. Okay, so there are 20 different amino acids. Okay, your proteins are made up with maybe hundreds of those amino acids. Okay, so it's the same thing. I told you whatever this case, this amino acid, okay, can become these different charge conformations. So at the very low pH, it may be positively charged because of that NH3 plus. Okay, and then if you bring up the pH, hydrogen ions are going down, then it may be neutral because of these two plus and minuses. And then if you remove more hydrogen ions, then what? you have maybe a couple of negatively charged here, so overall it's going to be negatively charged. If you deplete more hydrogen ions, then also the negative charge, this can become neutral, so you will have more negative charge overall in this amino acid. So your amino acid can become 1, 2, 3, 4 different charge composition. That's what it shows, right? So in this case, pK1, pK3 divided by 2, so pi value is pH of 2.7, so that's what it means. Okay, anyway, so that's not important. So the important thing is, out of 20 amino acids we have, okay, there are different pi values for all those amino acids. Okay, so glycine, for example, it is neutral at pH about 5.97. Okay, on the other side, leucine is about neutral at pH 5.98. Okay, aspartic acid is about neutral at pH 7.2. That's why it's called acid. And glutamic acid, again, at pH 3.2, it's neutral. Lysine, arginine, these are basic amino acids. So at these basic pHs, their pi values are set. Okay. So if you think about overall your protein, okay, proteins are made up of maybe hundreds or thousands of different amino acids. So you need to know the pi values of all amino acids, and you need to calculate out by combining all those pi values at what pH value your protein will be neutral. Okay, so you need to understand that. Once you know that, then under what pH buffer condition your protein will be negatively charged or positively charged, you have to be able to predict that. Okay, otherwise you cannot apply ion exchange chromatography method. Okay, the reason is you need to know if your protein will be negatively charged or positively charged in order for you'll be able to capture your protein, right? If the overall net charge of your protein is negative, that means what? You will have to use the resin that is positively charged. Then you will be able to capture your protein. Okay, if it's the other way around, if your protein is, positively charged or negatively charged, then you have to use opposite, charge resin. So you have to be able to predict how your protein will be charged. Okay, so that's why we need to talk about this, pH influence on your protein charges. Okay, then how do you predict how your protein will be charged? So this is a handy kind of graph that can allow you how you can predict the charge of protein. Okay, in order for you to use this graph, you have to know the overall pi value of your protein. Okay, so by calculating out all the pi values of the amino acid composition of your protein, you can find out at what pi value your protein will be neutral. Once you know that, then you can use this graph. Okay, on this graph, so y-axis is positive or negative charge, and x-axis is the pH values. Okay, so pH values from 1, maybe 0 to all the way to maybe 14 right here. Okay, and then here you will identify the pi value of your protein. Let's say your pi value of the protein was maybe 9. Okay, that's the pi value of your protein. That's where your protein will be neutral, no charge, right? pH 9. Okay, and then you're going to draw inverse S on your graph. Okay, and that S graph, the line will go through your pi value of 9 there. Okay, so inverse S, so it goes down and going through 9 and comes down here. Okay, so what does this do? And this graph will now allow you to predict the charge of your protein. So let's say your protein is dissolved in a buffer that has pH value of 9. Then what? Its overall charge will be what? Neutral. It's not charged, right? However, if your protein is dissolved in a buffer that has a pH value of, for example, 10, then how is it going to be charged? It's going to be slightly negatively charged. Okay, so what if it's dissolved in a buffer that has pH value of maybe 11 or 12? Then your protein is strongly negatively charged. Make sense? And what if your protein is dissolved in a buffer that has pH value of 8? That is positively charged, slightly positively charged. If it's 6, more strongly positively charged. Does it make sense? So if you use this graph, then you can predict how your protein will be charged under certain pH buffer condition. And once you know that, then you can determine, okay, if my protein is positively charged, then I have to use what? cation exchanger column, okay, that will have the resin that is anion. So that's how you can develop your chromatography method. Okay, so you should be able to predict how your protein is charged. Based on that prediction, you can choose the correct ion exchange chromatography medium. Okay, so that's the most important information here. So for example, you are running an anion exchanger. That means your protein is an anion, so the resin is a cation, right? So you're going to use a buffer like this, maybe starting buffer, binding buffer, washing buffer. pH 8, okay, is what you're going to use. If you go back, pH 8 is around here, so it's positive charged, right? So yeah, pH 8, 3 Cl, pH adjusted to 8, and you have a little bit of tree salt in there, 20 millimolar, which is not giving you much charge there. Okay, and then washing and dilution buffer, you will add more salt in them, but pH should stay the same because your protein should have the same net charge. In this case, maybe cation charge or anion charge. Okay, the anion exchanger in this case. The dilution buffer, the difference between starting buffer and dilution buffer is what? The salt composition. So starting buffer has very low salt, almost no salt in there, but dilution buffer has what? How much salt? 1 molar salt there. So it can break open the target bound proteins from the column. You can elute it out. Cation exchanger typically made out of this. So pH composition is different. The pH 8, now pH 6. Okay, lower pH. So to make sure that your protein is a cation binding on the anion resin. So binding buffer, almost no low salt. Okay, and then elution buffer at the high salt here, 1 molar sodium chloride again. Okay, but pH should stay the same. Okay, so that's how your anion exchange chromatography run or a cation exchange chromatography run will be done. And again, so this is a chromatography system makeup buffer. We already talked about it. And then so the chromatogram, if you are doing an anion exchange chromatogram, you will see something like that. You already saw this. 2-column volume up, maybe sample loading, and then you do the washing, okay, by increasing what? The salt composition. So red line is the conductivity, right? It's going up. And then you're doing an elution at the high salt, maybe 1 molar salt. Okay, sodium chloride is added. Then your target protein peak came off. That's a eluted fraction. And then salt is brought down back again. So maybe your column can be recycled. Okay, sample loading, washing, elution, and column regeneration. 4 main steps. Okay, so that's what it looks like. And there are molecules that are not wanted coming off from the column. These are washing fractions. You don't want these proteins, but the one protein you want is this one. And another example, again, it's ion exchange. You can see the buffer change, low salt, washing, high salt, and coming back, column regeneration, right? And in this case, 3 different peaks are coming up, very small peaks are coming up. This is probably not a good ion exchange chromatography method because you don't see anything captured on the elution step. So this is not a good method, but I'm showing you an example of the chromatogram there. Another ion exchange chromatography method, the same thing, the sample loading at the low salt, washing by increasing the salt, and dilution at the high salt. But the difference between here and here is what? The washing, how it's done. This is a continuous increase of your salt composition during your washing step, but this is what? This is a kind of step gradient of your washing. That's what it is. You only use 2 different washing buffer here. 1 washing buffer, 2 washing buffer. You just change the buffers suddenly. So, but still it works as a washing step because you know there are only 2 proteins that are washed away from your column. You know what under what buffer composition they are coming out. If that's the case, you don't have to slowly increase the buffer. Instead, you just switch out your buffer to get rid of these. And then this is the probably target protein eluted at the higher buffer condition. Okay, so that's the ion exchange run. Okay, so take a look at this animation. It'll explain you how this ion exchange chromatography method will work. And it's going to show you sample loading, washing, and elution step, and the column regeneration. Take a look at that.